So in this lecture, we'll look at more SN2 reactions, and we'll look at some additional characteristics of SN2 reactions. So in the first lecture, we looked at these first 5 characteristics of an SN2. So the rate is dependent on both the nucleophile and the alkyl halide, so it's a bimolecular reaction. Good leaving groups, so iodide's better than bromide, better than chloride. It's a concerted one-step reaction. No rearrangement is possible. So we didn't talk about that in the last video. I just added that here so that when we contrast this to an SN1, that will make sense what that means. For the alkyl halide, right, it's got to be methyl primary or secondary, can't be tertiary, because those are too slow for steric reasons. You need a good nucleophile, or let's say a strong nucleophile, and you just have to memorize what those are. And so in this lecture, we'll look at the stereochemistry of an SN2 reaction and how does a solvent affect an SN2 reaction, or what's a good solvent for an SN2. Okay, so if we took this alkyl halide and we reacted it with, let's say, what's a good nucleophile to pick? Let's go with so if we reacted with that nucleophile. So first of all, characterize the conditions. Is this the conditions for an SN2? So how would you classify your alkyl halide? It's secondary. That's fine for SN2. It's not ideal, but it's fine. And then your nucleophile is a strong nucleophile. So that's the conditions for an SN2. So what's going to happen in an SN2 is this sulfur is the nucleophilic atom. It's going to attack the carbon that's got the leaving group, and you're going to break the carbon-bromine bond. Okay, so this is sp3 hybridized, right? So it's tetrahedral. And when the nucleophile attacks, so the nucleophile must attack from the opposite side of the leaving group. Okay, so if we so the nucleophile has got to come in and displace the bromine, and if we sketch the transition state when that happens, so we're breaking the bond to bromine, we're making a bond to sulfur, and the ethyl group is attached to sulfur, is just along for the ride. Oops. And so what? So you go through this trigonal bipyramidal transition state, so you can think of this like an umbrella. Flipping inside out, so then the nucleophile, so if the bromine is over here, the nucleophile comes in here, and then that flattens out. And then when this bromine finishes leaving, then it flips inside out like an umbrella, and then the nucleophile is attached over here to the opposite side that the bromine left from. Yeah, I'm not sketching this very well. Anyway, let me try this again. Okay, so our stereochemistry was at R or S to begin with. So bromine's priority 1, that's 2, that's 3. 1 to 2 to 3 is clockwise, so 4 is in back, so the arrow stays clockwise, so this is the R isomer. So let me make sure I draw R here since I'm changing my perspective. That's a better picture. Okay, so nucleophile's got to come in from the backside. And then that carbon's got to flatten out in the process. And then when you finish breaking the carbon-bromine bond and finish making the carbon-sulfur bond, then sulfur would end up on the opposite side from where the bromine left from. So now if we assign stereochemistry, so sulfur's priority 1, that's priority number 2, that's priority number 3, and now and 4 is in the backs, so the arrow stays, in this case, counterclockwise. So we started R, and we ended up with the S stereochemistry. So this is a characteristic of an SN2 reaction. Is that you get inversion in stereochemistry. And that's because the nucleophile bond to the nucleophile has to make at the same time that the bromine is leaving, and the nucleophile has to come in opposite of the bromine. Okay, so stereochemistry, so you get inversion. Of stereochemistry. So let's take a few examples to try to illustrate that. Okay, so if we took that alkyl halide and let's say we take potassium iodide as the nucleophile. So is this an SN2 reaction? We'll classify your alkyl halide. It's secondary, right? That's a secondary carbon, and that's a very good nucleophile. So that's the conditions for an SN2. So for the SN2, then the nucleophile has to come in the backside, the opposite of the leaving group. So iodine's got to come in there, and the chlorine's got to, and then the chlorine leaves. And so when this happens, then the hydrogen is going to flip down into its place. So that's the inversion. So when chlorine leaves, then your product is going to look like. So now iodine is there, and hydrogen. So chlorine started equatorial, and the hydrogen started axial. And now the hydrogen is equatorial, and the nucleophile has to be axial. So this is not a chiral carbon, right? But you still get you always get inversion at wherever the nucleophile attacks in a SN2 reaction. Although there is stereochemistry involved here, right? So is the starting material cis or trans? So let's see, hydrogen is on top of chlorine, but tert-butyl is on top of hydrogen. So you started with a trans isomer, and then hydrogen's on top of, iodine's on top of hydrogen, and tert-butyl's on top of hydrogen. So you ended up with the cis isomer. So you inverted the stereochemistry in this case as well. Okay, so there's lots of ways to illustrate this if you're given a reaction problem like this. And let's say your nucleophile was azide, so maybe something like potassium azide. Doesn't really matter what the cation is. So again, convince yourself that this is the characteristics for an SN2. Classify the alkyl halide, so that is secondary, right? And that's a good nucleophile. So this should do an SN2. So what's got to happen is you have to invert the stereochemistry. So the easiest way to illustrate this is place the nucleophile opposite of where the leaving group was. And so if we assign stereochemistry, you can see that it was inverted. So 1, 2, 3 is clockwise. This is the R isomer. And then 1, 2, 3. Now you have the S isomer. Okay, one more example. So I give you all of my secrets here. Let's see. Not that. That's not going to work because that's tertiary, right? That what I drew would be a tertiary alkyl halide, so you can't do an SN2 with that. So let's change something here. Now it's secondary. All right, just secondary, not allylic because it's too far away from the double bond. And if we, so our nucleophile, so let's make that our nucleophile. Okay, so you know secondary and a good nucleophile has to do an SN2, so it means, and that's a chiral center, right? That's the carbon with the leaving group is attached is chiral. So you know you're going to have to flip the stereochemistry. So if you flip two things, that changes the stereochemistry, right? So if we flip the hydrogen in the bromine's position, that would change the stereochemistry from R to S or S to R. So if we put the nucleophile where the hydrogen is and put the hydrogen where the bromine was, that would flip the stereochemistry. So it doesn't matter, or we could move this group over to there and put the nucleophile here. Or we could put the nucleophile here and we could move that to where the bromine is, doesn't matter. As long as you only switch two things, that changes the stereochemistry. So if I put the nucleophile here and put the hydrogen in the place of where the bromine was, that would be the opposite stereochemistry. So that would have inverted the stereochemistry. And so again, basically all that's happening is this oxygen is the nucleophilic atom. It is attacking this carbon and it's kicking off the bromine. Okay, so that's some examples of SN2 reactions where the stereochemistry has been inverted. Or in more simple molecules, if we had that, for example, with a nucleophile, so that's a secondary and benzylic alkyl halide, and that's a good nucleophile. So sulfur is going to attack this carbon and kick off the iodine. That's a chiral center where it's reacting at, so you need to show the stereochemistry flipping. So move the hydrogen to the front and attach the nucleophile in the back. And then whatever's attached to sulfur is just along for the ride. So that would be one way to illustrate the product and illustrate the inversion of stereochemistry also. Okay, one more example of this. Okay, how would you classify the alkyl halide? So that is a secondary alkyl halide. Cyanide's a good nucleophile. So this can do an SN2. So CN's going to attack this carbon, kick the bromine off. So flip the hydrogen to the front, that would be the inversion, and attach the nucleophile to the bottom. and that would be the product. Okay, and so you might ask yourself, well, this is a chiral carbon. So why didn't we invert the chirality there? And the answer is because there's no reaction there. So since there's no reaction at that carbon, you don't have to do anything to it. Nothing's going to change there. The only thing that's going to change is where the reaction occurred at, right? Okay, and then last concept in this for the SN2 reaction is the solvent. So let's say you did this reaction. Let's pick potassium. What's a good nucleophile to pick? So let's pick a nucleophile. Let's say potassium OCH3 minus, and then let's throw a solvent in. So maybe the solvent is water. And then let's compare that to so same alkyl halide, same nucleophile, but let's just change the solvent. So this would be a typical solvent for an SN2. It's called DMF. Which is just an acronym for dimethyl formamide. Okay, so if we did this reaction, then the reaction that is much better is this one. So this is going to be a faster reaction, probably give you better yields. And the difference is because of the solvent. So this would be what's known as a polar protic solvent. And this would be what's known as a polar aprotic solvent. So why is water a polar protic solvent? Well, it's polar because it has a dipole, right? Oxygen's partial negative, hydrogen's partial positive. And so oxygen pulls electron density off of hydrogen, and then the molecule has a net dipole moment. And furthermore, it has partial positive hydrogens. So it's acidic. So the problem with a nucleophile like this is, so if we take our nucleophile, and so that's the nucleophilic atom. All right, so for this reaction to work, we need a lone pair of electrons on oxygen to attack this carbon and kick off the bromine. But what's this nucleophile going to look like in water? So if we have a water molecule, well, because the hydrogen's partial positive, it can make hydrogen bonds, right? You can make hydrogen bonds to any of the lone pairs or all of the lone pairs on oxygen. And if the lone pair of electrons tied up in hydrogen bonds, then it's less nucleophilic. So that's going to hinder an SN2 reaction and make that reaction proceed slower. But you do need a polar solvent. So if we contrast this, if we add to this reaction as well, so same nucleophile. But what if your solvent was something like hexane? Which would be an example of a nonpolar aprotic solvent. Well, so the problem with this would be, would you expect the nucleophile to be soluble in hexane? And the answer is no, because this is very polar. and this is very nonpolar. So your nucleophile doesn't dissolve. So if you set this reaction up, so that's your hexane. So you may get some solubility of the alkyl bromide, but your nucleophile would be in a solid state, not dissolved, and so that makes it hard to react with your alkyl halides. So nonpolar solvents are not good for SN2 because you'll typically have very polar nucleophiles that you need to dissolve. And protic solvents are not good for SN2 because they hydrogen bond to the nucleophile and decrease its nucleophilicity. So polar aprotic solvents are ideal. So this is polar, and that's going to help dissolve. But it's aprotic, so it won't hydrogen bond to it. So it won't stabilize the nucleophile and make it non-reactive. So why is DMF polar? Well, obviously oxygen's partial negative, carbon's partial positive, nitrogen's partial negative, right? The molecule has a dipole moment. So it's a polar molecule, and that's going to help dissolve the nucleophile, which is polar. But all of the hydrogens are on carbon. In your solvent, so none of them have a significant partial positive charge, so they can't hydrogen bond to your nucleophile. Okay, so some typical SN2 polar aprotic solvents. So we saw DMF. So let me sketch them out and then we'll name them. Okay. Yeah, so this would be some typical polar aprotic solvents. Here's another good one. So this is acetonitro. Acetone, right? It's fingernail polish remover. This molecule is known as THF. So THF, and this molecule is known as DMSO. This is acronym for dimethyl. Right, there's your dimethyl. Dimethyl sulfoxide. So that's a solvent that I hate to use. I hate working with. It's really good at dissolving organic molecules, but it will absorb through your skin. And anything that's dissolved in the DMSO will absorb through the skin with it. So sometimes medicines are actually dispensed this way. Dissolve it in DMSO, and then you can rub it on your skin, and it will absorb through your skin and take the medicine with it. This is used in livestock, so sometimes medicines are dispensed to horses, for example, that way. But I absolutely hate using the solvent because that can be dangerous, right? If you have something that's toxic dissolved in DMSO and you happen to get it on you, then it can absorb through your skin that way. But I hate it because it will eventually, when it absorbs through your skin, it'll eventually get into your mouth and you'll taste it and smell it on your breath. And of course, compounds that have sulfur in them typically don't smell very well. So not a very pleasant solvent, in my opinion, to work with, although it's a really good solvent in organic chemistry at dissolving things. Okay, so anyway, when we do reactions, SN2 reactions, so I would typically just write a reaction like that and not I typically don't show the solvent. It's there. You need it for an SN2 reaction, but I oftentimes, and chemists oftentimes don't show the solvent. It's just understood that there's a solvent there. And another reason I typically don't show the solvent is because it just confuses students, and they want to attach it in some way to the molecule. For example, if I did this on a test, and then a student may think, oh, I need to use this some way. The student may not recognize it's a solvent, and they may start doing crazy stuff like attaching the sulfur, and just totally wrong. So sometimes I don't show the solvent just to not confuse students, but you should know what the solvents are so that you're not confused, because I may throw a handful of examples at you with the solvent in there just to see if you can recognize the solvent. And so for all practical purposes, you just ignore the solvent. So if you're given this reaction, then you would just recognize that's DMSO, which equals the solvent, and basically means ignore it. In terms of predicting the product, all that you'd want to recognize is CN's the nucleophile. It's going to attack there and kick off the chlorine, and that's your product. The solvent is just there to dissolve things. All right, so you may see the structure of the solvent drawn out. Or you may see it wrote out like that. So you just have to recognize that's the solvent. You can just ignore it in terms of predicting the product. And just recognize that's the nucleophile. So just substitute the nucleophile for the leaving group, and that's your product. Okay. And that's it for the SN2 reaction.